für 5 minutes. You got it. All right. Our next speaker is Hitesh Kishoridas. Please take it away.
You?
No, press the button.
This one?
Yeah.
Okay. Perfect. Is my cursor still on? Okay, never mind. Thanks everyone for being here, and thanks to the organizers and the participants for the excellent Thinkshop. I'm Hitesh. I'm a finishing PhD student in at MPA in Max Gronke's group, which is soon be moving to Heidelberg. And today I will be talking about sort of the multi-phase dynamics in context of simulations in a turbulent CGM, also with magnetic fields. So there have been already a lot of nice review talks, both on the numerical or theoretical side and the observations. So I don't have to go through the introduction too much, but I will still try to point this out specifically that so multi-phase gas dynamics is sort of a particularly hard problem to solve because of its multi-scale nature. There have been simulations at small scales. I need to start the timer, sorry. It is already started. Which sort of show that the more you resolve, the smaller and smaller structures we start to see. And it sort of structures all the way down, and sort of you always are not resolving some smaller scale stuff. And it becomes a bigger problem when we are trying to sort of use simulations to have predictive powers, because there are small scale effects that Max sort of presented yesterday in his review talk about cold gas survival, which can have a significant impact on large scale behavior, like the baryon cycle and the different observables that Saline also introduced today. But there is a big scale gap between these two. And we cannot really brute force our way through it, because if you try to resolve these small scales in the large scale simulations, if you do like a back of the envelope calculation, you'll find out that it would take decades, if not centuries, to run these on exascale computers. So a way around these could be subgrid models, which are essentially models or theoretical frameworks which keep track of processes happening at scales smaller than that are being resolved in the simulations. And to that effect, what our plan has been during my PhD here and in general is to run these idealized simulations, which are some small scale simulations where we can resolve significant amount of physics and can sort of make theoretical frameworks which can later sort of influence subgrid models, which can then again in turn be implemented in large scale simulations, and that can be used to have a better predictive power in these large scale simulations. So I'll talk about these setups called turbulent boxes, where we have a box, like a periodic cubic box, where we drive turbulence in hot phase. So this is the virial 10 to the power 6, 10 to the power 7 Kelvin gas. And we introduce a little bit of cold gas in there. So during the whole talk, whenever I say cold gas, I'm referring to 10 to the power 4 kelvins. And we sort of let it evolve and see what happens. This was studied by Max way back in 2021. And what they found was that if the cold cloud is smaller than a certain critical radius, the turbulent mixing wins and the cold gas is mixed away, then the whole gas becomes hot. While if it is big enough, the cooling wins, and the cold gas can grow and survive for longer. But there's a big elephant in the room here, because what about magnetic fields? And it's been known from both like theory and simulations that if the mixing between the two phases is happening because of this mixing layers between the sharp mixing layer between the two phases, with magnetic fields, this would be strongly suppressed. Like on the right side, you can see one of the simulations that we ran where with magnetic fields, you can see the intermediate temperature gas is much less compared to without magnetic fields. So this can affect the evolution significantly if there's a difference between the with and without magnetic fields. And we wanted to test exactly that. So in this project, we sort of drove MSG turbulence. So we introduced magnetic fields and let it evolve, and then introduced the cold gas cloud. And you can, on the right side, you can see sort of the evolution with and without magnetic fields. The amount of cold gas looks similar. I'll get to that right in the next slide. But one thing I would like to mention is the structure of the cold gas. With magnetic fields, it looks much more filamentary and might remind you of what Marcus was mentioning in the discussion session yesterday, that with magnetic fields, the cold gas seems to be much more filamentary. I'll get to that again later too. But we wanted to quantify the cold gas mass, and we find that the survival and the destruction of this cold gas cloud that I was talking about earlier, if the cloud is small enough, then it gets destroyed, is unchanged with the magnetic fields. So the circles are the cases where there is no magnetic field, and the corresponding diamonds are the same simulations just with magnetic fields. And we find that both, if the one with magnetic fields doesn't survive, sorry, the one without magnetic field survives, the one with magnetic field does too, and the same when it gets destroyed. So there is no change with the introduction of magnetic field. And how we made sense of this, because just a few minutes ago I said that we expect there to be a lot of differences, is by saying that it's not the small scale mixing layers which are doing most of the mixing. It's the larger scale turbulence which is sort of twisting and sort of folding these cold gas structures and resulting in the mixing. So we don't have to worry about the mixing layers that much. It's the overall turbulence that we have to worry about. So that's good. Now we have a simulation which has MHD multi-phase turbulence. What we wanted to look at next was the magnetic field structures. This we were interested in because in one of the other conferences, this talk about sort of cosmic ray transport came in, and we thought this could be something which can have implications to these effective cosmic ray transport models. So to look at that, what we did was we followed the field lines for, say, a length of L stream, and we see how far we made it. And taking the ratio of these two, you can sort of define something called an entanglement. And higher the entanglement, the more sort of wavy the magnetic field line is. And you can repeat this experiment with many streamlines going farther along the magnetic field. And what we found that the longer you follow the streamlines or the magnetic field lines, the higher the entanglement is. And if you think about it a little bit, it turns out that this refers to the fact that the magnetic field lines are fractal in nature. Of course, still the dissipation length scale, which in our case is the grid scale. And this was an interesting bit of conclusion that we found, and could have some implications. And the next thing that we looked at is something very relevant to what Celine showed just in the previous talk, which is we wanted to see if there is an observable difference between the case with magnetic field and without magnetic field. And to do that, we wanted to look at Mach quasar absorption features. Specifically, we used Trident to make Mach absorption spectra, about 10,000 of them, through one of our boxes, which had column density similar to what we expect in a CGM environment. And we looked at magnesium-2. We also looked at carbon-4, but I will mostly showing the magnesium-2 results. What we tried to compare it with was this paper results from Churchill 2020, where they use HST cost data to compare the number of magnesium-2 features in a complex with the total equivalent width. Unfortunately, we don't find a difference between the case with and without magnetic field, so they were almost indistinguishable, but both of them seem to match the Churchill 2020 result, which was kind of surprising given how simple the setup was. And we saw a very similar relation also with our carbon-4 Mach spectra, and even with different spectral resolutions. So this could sort of point to like a more fundamental origin of this relation. So there have been more studies. So this was with magnetic field. We have also looked at what happens if we add more phases. But what I would like to talk next about is the subgrid models. So we can take all the understanding that we got from the idealized simulations and try to make the subgrid models that I've been talking about for a long time now. The method that we went for was this multi-fluid methods that Rainer introduced yesterday, where instead of having just one density, energy, or momentum in each cell of a simulation, you have multiple, and you keep track of them with this volume filling fraction, which gives you this ratio of how much of first fluid do you have versus the other one. And we use the repo code, the multi-fluid module written on top of it. And the overall problem statement was that, okay, we have this high resolution benchmark idealized simulations. Now, with the subgrid model, we should be able to run like a much lower resolution box with the subgrid model, and they should behave very similar. Thank you. Similarly. And this should also keep track of both resolved and unresolved clouds, because in simulation, sometimes you run into cases where you're actually resolving the cold gas structure. So this is sort of the framework. So we have the hot gas as one fluid, the cold gas as another, and there would be interactions between these two. So the subgrid model is what is giving the mass, momentum, and energy exchange between these two fluids. And that's what we did. So I would like to introduce our subgrid model, Mowgli. It's referring to this, for people who may not know, is to this character in Jungle Book, which is pretty popular when I was a kid. So what it gives us is all the interaction. Oh, oops. What did that do? That gives us is the interaction terms because of different physical interactions. So there can be drag forces because these two fluids are moving again, like in relative to each other. There is turbulent mixing because the the cold gas mixes away into the hot phase. And there's cold gas growth because the hot phase afterwards cools and gives rise to some cold gas. So we include all of them, and we test them against this benchmark Athena++ simulations across a very wide parameter space. We have different turbulent velocities, we have different resolutions, if the cold gas cloud is resolved or not, and with and without without cooling. And we repeat this until we get a model which is as physical as we can get it to be, and with as fewer tunable parameters as we can. And we managed to get that. And the tests that we did was, I'm just showing an example. We tested the turbulent mixing rates by calibrating it without cooling, which is important for the small cloud cases that I showed earlier, that the small cloud should get mixed away in the hot phase. And we tested the cold gas growth rates against this benchmark simulations by using this larger cloud simulations where the cold gas should grow. And there are different properties that sort of essentially emerge out of it, which I will maybe skip for sake of time. So we find that the subgrid model is able to sort of consistently recreate the unresolved cold gas behavior when we compare it to these resolved simulations. So what can we do with this? So here is a sort of a very simple showcase sort of simulation that we ran where we have 100 clouds. All of them are physically big enough that they will grow, but they are computationally, so numerically small, as in they're small enough that they are smaller than the simulation cells. So they are not resolved by the grid structure. They are all unresolved clouds. Oh, thank you. All unresolved clouds which will grow. And if you wanted to do this with like Athena++, which is like and try to brute force your way through it by resolving the small clouds, it would take 5,000 cube cells, which can be, this is a serious simulation that you have to run and takes ages to run. But this is just a 64 cube cells simulation with the multi-fluid subgrid model, and takes about an hour to run. And the hope is that in the near future, it would be possible to run a zoom-in simulation or a larger scale simulation where the cold gas is consistently kept track of, and we don't have to really brute force it to get the cold gas consistent. And so that's sort of the idea, that the Mowgli sort of fills this gap between the two scales and sort of connects them a bit more consistently. So what's left? There's a lot of things that these are sort of all the sort of stuff that we have been working on. But there are a lot of things which are missing in the idealized simulations. It's a very rich area where there are a lot of things that we still don't understand and is missing in the theoretical framework. There are also things that can be improved in the subgrid models that we are also working on. And of course, we can run larger scale simulations with these things once we get there. And I will end with my key takeaways and a poem from ChatGPT. Thanks.
Right, questions? There's one. In the middle.
I have a naive question maybe. In the highly resolved case, you showed a lot of structure. And then in the Mowgli result, it was the cold gas was kind of covering the entire cell.
Right.
So that may be appropriate for the fraction of cold gas, but does it also then reproduce the kinematics? So if you would like observe it with a Mach spectrum, would you see the same kind of width of the lines?
That's a good question. So what I was showing there was like a projected volume fraction. So even though it looks like it fills the gas, it's just saying that the cold gas is the dominant mass component in the cell. So it's not exactly one-to-one like by eye, but the question about the kinematics, there is some assumption going in which tells us what the underlying structure is in the cell. It's part of the model. And that's something that we would have to verify also when we go on to try making mock absorptions on a subgrid model. So that's something that we have to verify later on. But there is a model that we can make from each cell. There have also been sub-analytic, like semi-analytic models, like from Datta and from Cameron Hummels, where they also looked at something similar, trying to take an unresolved simulation and fill in the gaps using like a model on top of it. Yeah, thanks.
All right, we have one question online.
It's from Martin Fournier, and his question is, so he writes, turbulent box simulations of multi-phase gas seems to result in very different morphologies depending on whether there are magnetic fields or not. But this does not seem to result in different clump mass distributions, slope of -2 in any case. Isn't that surprising?
It's sort of, that is true. We don't know if I could, I don't know if I can explain why exactly they don't change. My explanation would be, I think once you have, because the masses are the same, the growth rates, they don't change. So the overall total mass is the same. It just somehow turns out that it ends up being the same, also the same distribution. Maybe, yeah, that might have to do with the fact that the turbulent structure is similar in both cases. But yeah, sorry, I don't think I have a clear answer to why exactly it's this. It's not necessary that it has to be the same. Yeah. Thanks.
All right, I think Ellen was first. I don't know where the microphone.
So it was very, very interesting. I'm not going to ask you about magnetic fields. I'm going to ask you about clumping. So if you have a radiative diagnostic that depends on n squared, it'll be very sensitive to the clumping factor. And do your unresolved models work? Does Mowgli work as well as a resolved simulation in getting the right distribution of n squared?
So that's a good question. I skipped this part where we did test this. There it is, the cold gas dispersion. So we started off with cold gases in the middle and see how it disperses. And we found that it matches relatively well. Although when the cold gas is not resolved at all, it's a bit more dispersive because of the numerical method. But we do seem to get a similar spatial distribution with the subgrid model and the unresolved cases. So they do seem to agree with each other relatively well. The sort of logic behind that is sort of that most of the dispersion is happening because of turbulence. And if we are getting the large scale turbulence resolved in both cases, the turbulent dispersion works out, and then the density distribution also works out relatively well. I don't know if I answered the.
Did you also compute the clustering factor, clumping factor for the resolved and the unresolved case?
Clumping factor, no, we haven't checked that yet, but that could be something. Right, okay, thanks. That's something we can check for sure. Thank you.
I saw Jonathan's hand up, and can the next speaker already come up?
That's Jonathan Stern, Tel Aviv University. So very neat simulations. So I have a question about the predictions. can you, in this two-fluid approach, can you also predict the intermediate ions like carbon 4, for example, or do you maybe from the transfer terms? Yeah.
It is possible in a way that we know how much mass transfer happens. So we can use the amount of mass transfer to estimate how much intermediate intermediate gas would be. And that can be used later on for making the intermediate ion estimations. I think that should be possible. Thanks.
All right. Thank you very much, Hitesh.